Morning, everybody. Thank you for having me. My name is Jim. I'm a professor at Caltech. I broadly study stars and stellar astrophysics. Today, I'm going to focus on massive stars, but I really just want to pause to note the amazing progress that's been made in low-mass stars over the last decade or so. We don't have many talks about it at this conference, but we've been able to do amazing things largely because of astroseismic data, Gaia, various wide-field spectroscopic surveys. For low-mass red giants, we can now do things like measure their masses and radii incredibly precisely. That's allowing us to measure age, which is super important for all these galactic evolution studies. We can measure things like what is happening in their cores, which nuclear burning phase is happening, what their core rotation rate is, and we can even measure magnetic fields inside the cores of these stars, which is 1% the radius of the star. And we can actually do that. This is something we never dreamed of. So there's been enormous progress. In high mass stars, it's a little more difficult, but still a lot of interesting things have happened. One of the really amazing pieces of data is various types of transient data. So gravitational waves have obviously been a big discovery. Also, various transient surveys are finding all kinds of explosions of massive stars. So this is a plot showing various types of supernova that were observed. This is the ZTF sample, but there are other surveys. So we see various types of core collapse supernovae, which are explosions of massive stars, and we have all these different subtypes, and this is all related to things like mass loss from these stars and binary processes. In this talk, I'm going to be focusing on the most common type of core collapse supernovae, which are type 2p hydrogen-rich supernovae. These come from explosions of red supergiants. So I'm going to be talking about the mass loss of those stars. For hot stars, like main sequence O and B type stars, we understand to first order what the mass loss mechanism is. It's basically photon pressure on a forest of absorption lines produced by iron group elements. Basically, those elements are super Eddington and get blown off the star. So the mass loss rates, this is a prediction. They scale with the luminosity of the star. Typical mass loss rates for like an O star is 10 to the minus 7 solar masses per year or so. There's some uncertainty. There's a factor of few uncertainty, I'd say, due to things like instabilities in the winds, which make the predictions more complicated, also make the interpretation of data more complicated. But at least within a factor of a few or so, we understand those winds. For cool stars like red supergiants, I'd say it's even less clear what's going on. The basic picture, and by the way, this is similar to the basic picture for mass loss from red giants and AGB stars, is that in order to drive mass, you need to form dust, right? Because these stars don't have those same absorption lines. In order for photons to be able to drive away a wind, you need to form dust, which is very opaque. The problem is the surfaces of these stars are too hot to form dust, so you have to lift material a few stellar radii above the surface in order to get it to cool and form dust so that a wind can be driven. So you actually have to do most of the work. You have to lift this material most of the way out of the potential of the star before you actually really start launching the wind in earnest. So the question is, how does that happen? The viewpoint I'm going to be discussing is basically shocks that are launched from the surface of the star that go up and support a dense chromosphere in these stars, which supports the wind. One of the things that has helped with these kinds of studies is there are large spectroscopic surveys of stars, especially in the LMC and SMC. A lot of this has been done by VLT, but also I think this study uses WISE measurements and Spitzer data. What people can do is, for large samples of red supergiants, measure the mass loss rates of red supergiants. These are all in the LMC. This is a study by Antoniadis. What has become clear in a few studies is that it looks like there's a kink in the mass loss rate. So there's this kind of shallow increase in mass loss rate up to a luminosity of a few times 10 to the 4 solar luminosities, and then a steeper increase in the mass loss rate. So this is definitely a clue as to the physics of what's launching these winds. And this is super important for understanding the explosions of these stars. Like I said, red supergiants produce the most common type of supernova, which are type 2p supernova. So this is a light curve of a well-observed supernova. What these supernova look like is they have a plateau. The 2p stands for plateau. So they have almost constant brightness for about 100 days, and then they drop off. These are actually not nickel-powered supernova. They are predominantly powered by just the thermal energy deposited into the stellar envelope by the shock wave driven by the supernova. But it turns out that the early light curves of these events and their spectra are super sensitive to the mass loss mechanism of these stars. So to see that, I mean, we've discovered many of these, and we've discovered them early, a few days after explosion or so from these transient surveys. And what you very often see is light curves that look like this. Say these circles are observations of this particular event. And if you try to match like a vanilla stellar model to these kinds of explosions, you get light curves that more look like these dashed lines. Basically, you can never fit the light curve very well. Another thing that you see in these events is you see often at very early times, so this is a supernova that was discovered within a few hours after its explosion, you see emission lines. In this, the H-alpha line is very prominent, but you see others. These you can also not explain with an explosion of just a red supergiant stellar model. The way you can explain both of these simultaneously, both the light curves and the spectra, is if there is a substantial amount of material just above the surface of the star, because that's actually what we're probing in the early early observations of these explosions. So people have done this for a variety of supernovae, and very often what they try to do is they try to infer the mass loss rate of these stars based on the density of stuff within a few radii of their stellar surfaces. And the mass loss rates you get are enormous. They're of order 10 to the minus 2 solar masses per year. This is more than a factor of 10,000 times larger than the measurements for typical red supergiants. So one of the interpretations that is very frequently advanced in the literature is that these stars have enormous mass loss rates right before they die. Part of the reason for this is at large distances, we also know from these supernova observations the density of the material can't be large. It's only large within a few stellar radii of the surfaces. So the density profile has to look something like this. This is the density profile of stuff around the star when it explodes. It has to be very large near the surface of the star and very low farther out. So one possible way of doing that is with some sort of pre-supernova outburst, some sort of enhanced mass loss. And I'm going to tell you, I think this is the wrong explanation. This is not what's happening, but it is partially my fault that this explanation has been advanced. I have written papers looking at ways of trying to do this. One of the ways is actually during the end of these stars' life, they have enormous luminosities due to nuclear burning in their core. And if some of that energy can be hydrodynamically transferred to the envelope, you can power large amounts of mass loss. I've looked at this in detail with my student Samantha, and the basic conclusion is most stars probably don't transport enough energy. It's too little too late to actually drive an outburst. There might be exceptions to this rule, but they are probably the exception, not the norm. So what is going on? Well, I think an important thing to keep in mind is that red supergiants are not nice spherical hydrostatic objects like we usually think about for stars. This is a nice simulation of a red supergiant by Jingze Ma. They probably look something like this. So they have enormous convective cells that are moving at a substantial fraction of the escape speed, and so the star's surface is boiling around very vigorously. These convective motions can be supersonic, and this is going to have important consequences for what happens both at the surfaces and above the surfaces of these stars. So the basic picture is that these convective motions, they launch shock waves that go out into the atmospheres of the stars because the density falls off, so these motions, the sound waves, steepen and become shock waves. And people have done simulations of both red supergiants. Actually, a lot of the best simulations have been done for AGB stars. This is a simulation of an AGB star. And you very clearly see these shock fronts that are sort of stochastically launched into the chromosphere, and they propel material outwards. We also see this directly. A lot of you may have heard about the great dimming of Betelgeuse. So this is a plot of the luminosity of Betelgeuse. Here's the great dimming. There was amazing data actually before and after this event. You can see right when the great dimming occurred is when the radial velocity of certain lines in the atmosphere of Betelgeuse was very negative. So that means we had stuff moving out. So the basic idea is that we had a shock wave moving out, propelling material. Some of that material got propelled far enough out to form dust, and then that dust obscured the star. So that's the basic picture. I'm going to advance for red supergiants and try to come up with a simple model for how much mass is actually supported in this chromosphere and how that sets the mass loss rate of the star. So there have been detailed studies dating back for decades looking at the density profiles that you expect from an atmosphere supported not by thermal pressure, but basically by a train of outgoing shock waves. It's actually the density profile you get is actually very similar to the density profile of an isothermal atmosphere. It's just that you replace the sound speed in this expression with the shock speed. And it turns out that the shock speed is roughly constant as a function of height. And so this density falls off basically in this super exponential fashion. But one thing to keep in mind is that we don't have a nice, well-behaved train of shocks. We actually have this stochastic mess. So what I've done is to consider a Kolmogorov velocity distribution of the shock amplitudes. And then when you integrate over that distribution, you predict a new density distribution. It's like a time or spatially average density distribution that you expect. And that scales exponentially with the ratio of the star's escape speed to the typical speed of these convective motions. For red supergiants, that's something like a factor of 10, this ratio. So that means the densities in these atmospheres are lower by a factor of e to the minus 10 relative to the surface. That's a small number, but it's still actually substantial relative to what you'd predict from other, for instance, just for an isothermal atmosphere. So these colored curves are this simple analytic prediction for what the typical density profile of these stars should be doing in their atmospheres. Orange line is a typical case. What you can see is that it's near the star, which the surface of the star, which is right here. This density can be a few orders of magnitude larger than the density of the wind that you would calculate if you assume it had a constant velocity and just extrapolated it all the way to the surface. And that's what supernova observers tend to do when they model these stars. So what I think is happening is that these large densities are basically the density of this chromosphere, which is in kind of quasi-hydrostatic equilibrium. It's not really the wind itself that we're seeing. The wind doesn't form until the dust formation radius, which is a few times or 5 times the radius of the star, roughly. So from this model, you can also predict what the mass loss rate should be. This is basically the same as a Parker wind. What you need is the density at, in this case, the dust formation radius, not the sonic radius. So you can take, basically you get this simple prediction for what the mass loss rate should be. These colored points are predictions from models of red supergiants for what that mass loss rate should be. And the gray circles are the data that I showed you earlier. And you can see that this matches the trend quite well. So I'd say this is quite encouraging. It can't match these low luminosity red supergiants very well. So maybe something else is happening there. Maybe some magnetically driven mass loss. The other thing you'll note is these stars are the mass loss rate of the star right before it explodes as a supernova. That can actually be a few orders of magnitude larger than when the star was burning helium in its core. And that's because these stars have actually expanded a little bit, their escape speeds have gone down, and so their mass loss rates go up. So I'd say this is a promising mechanism for explaining mass loss rates. It also may explain the supernova light curve. So this is some simple explosion models of our red supergiant models run by Daichi Suna, who's a postdoc at Caltech. The model without any chromosphere is this black line. The data we're comparing to a famous supernova 2023 IXF. The data is these green circles. You can see this model without any chromosphere totally doesn't match the data at all. But with a fairly dense chromosphere, so the orange or red lines, you get much closer. You broaden this initial peak at shock breakout, and you get much closer to explaining the light curves and probably the spectra of these events, although we haven't modeled that yet. So again, the picture is for these stars that above the envelope, we have some dense circumstellar medium, but that's probably not material that was ejected in some pre-supernova outburst. It's probably basically just the chromosphere, the dense chromosphere of these stars. And then farther out, you have the actual wind. So the nice thing about this model is it kind of connects both stellar models and mass loss rates and transient observations all at the same time, and it has some important implications. So for instance, the mass loss rates predicted by this model are quite high for high mass red supergiants. And so it predicts that any star greater than about 25 solar masses should lose its entire hydrogen envelope while it's a red supergiant and become something like a Wolf-Rayet star. We'll hear more about those stars later on. But this is a really important uncertainty in stellar evolution models, and hopefully this can help beat down that uncertainty. But this is a messy process. We need to do more detailed studies. There's a lot of things to follow up on here. So I will leave up these conclusions and take questions. Thanks.